for today, I'm going to explain quick integrals. Now, I have previously done a video in the past about long integrals, which I recommend you watch. I also recommend you watch my video from last week, which was about quick derivatives, because I will be referencing that. Now, quick integrals, like quick derivatives, are not only faster, but they are also easier. Now, there are actually two types of integrals: indefinite integrals and definite integrals. I'm going to start with indefinite integrals. Now, to explain how to integrate, I'm going to need a general function, and for this I will use x to the nth. Now, we want to take the integral of that, and we indicate that by writing an elongated s type thing, and at the end we write d and that whatever variable we're going to take the integral of. In this case, x. So this indicates that we're going to take the integral of x to the nth. Now, an integral is actually the opposite of a derivative, which is why it is sometimes called an antiderivative. So, if for a derivative, we take our function and multiply it by the exponent, and then subtract 1 from our exponent, for an integral, we do the opposite. We take our function and add 1 to the exponent, and then divide it by our new exponent. Now, there is one additional step with integration, and that is we need to add c. Now, this is because when you take the derivative of a constant, it is 0. That means that x squared minus 17, and x squared plus 158, the derivative of those functions is all 2x. That means that if the integral of this can be any one of these functions, we need to include the c to indicate that it can be any one of these functions. Now, usually when you're integrating, you'll have an actual equation that you're integrating. So, to figure out c, you can plug in the appropriate coordinates into your integrated equation, and you can figure out c that way. However, I'm not going to get into that. Now, before I get into an example of this integration, there is one last thing I want to show you. And that is, if you're going to take the integral of a function that has a coefficient. Now for this, you do the same thing as when you were taking the derivative of a function with a coefficient. You take the coefficient out and perform the process as normal. So, we'll take out the coefficient, and we'll do the normal integral, and we'll multiply the coefficient back in. And of course, add c. Now, I'm going to give an example of this, so you can generally see the process, and to prove that integrals are in fact the opposite of derivatives. Now, for this example, we're going to take 12x cubed and integrate it. So, since it has a coefficient, we will take the coefficient out. So we'll have 12 times the integral of x cubed dx. Now, so what we do is we add 1 to our exponent. So we have x to the 3 plus 1, or 4, and then we subtract it by, our new exponent. We then multiply in our coefficient and add c. Now, 4 goes into 12 3 times, so this can simplify to 3. So at the end, we get 3x to the 4th plus c. Now, in my quick derivatives video, I gave an example where if we took the derivative of 3x to the 4th, and I got 12x cubed. So as you can see, an integral is the opposite of a derivative. Now, on to definite integrals. Now, for indefinite integrals, you got an equation at the end. However, for definite integrals, you get a number at the end. Now, to explain indefinite integrals, I need to give a function, and for that, I will again use x to the nth. Now, we're going to integrate that, so we'll indicate such. However, there is something we need to add to this. Because this is a definite integral, we need to add limits. So I'm going to put x1 here at the bottom, and x2 there at the top. So this means we are finding the integral of x to the nth from x1 to x2. Now, for derivatives, you're essentially finding the slope. However, for integrals, you're finding the area under a curve. Now, for indefinite integrals, you are just finding the area at a specific point. You essentially have an equation that models the changes in area. However, for definite integrals, you're finding the area under a specific section. So we have our starting point and our ending point. So we are finding the area from x1 to x2. So we are finding the area of that. As such, we need limits to, know what section we're finding the area of. Now, on to the integral itself. Now, the first step of definite integrals is exactly the same as indefinite integrals. So, we'll go through, we'll have x to the n plus 1, and then divide that by the n plus 1. However, from here, these steps differ. For indefinite integrals, you would add a c and call it a day. You'd be done. However, for definite integrals, there are a few more steps. Additionally, for definite integrals, you actually don't need to add the c. However, to explain why you don't need to add the c, I'm going to add the c in anyways. Now, the next step for definite integrals is we need to put brackets around our newly integrated equation. And we're going to put then the limits off to the right. So now the next step here is to plug our limits into the variable. So that means we'll have x2 to the n plus 1 over n plus 1 plus c. And now we're going to subtract our other limit. So it will be minus x1 to the n plus 1 over n plus 1, then plus c. Now, if we distribute that negative, or this subtract sign really, we get a negative first limit and a negative c. Now, c plus a negative c gives us 0. So the constants cancel out. And that is why you do not need to include the c when you are figuring out a definite integral, because it just cancels out later. But nevertheless, cleaning this up, we will have x2 to the n plus 1 over n plus 1 minus x1 to the n plus 1 over n plus 1. So, if you're going to integrate the equation x to the nth from x1 to x2, you will end with x2 to the n plus 1 over n plus 1 minus x1 to the n plus 1 over n plus 1. Now, I'm going to give an example of this so you can better see what's going to happen. And for this example, I'm going to use x squared. X squared is a common one to use when doing calculus. And I'm going to find x squared from 1 to 3. So, to do this, we're going to just integrate x squared, and that will give us x to the 2 plus 1, or 3, and that's over 3. And then we have, from our limits, 3 to 1. So now plugging that 3 in, that gives us, gives us 3 cubed over 3 minus 1 cubed over 3. Now 3 cubed, that's 27 over 3, and then that's minus 1 over 3, because 1 cubed is, just 1. Now, 27 to the third minus 1/3 is 26 thirds, or 26 over 3. Now, if you watched my long integrals video recently, you may notice that x squared was the integration example I used for that. And at the end, I got 26 over 3. So, as you can see, quick definite integrals is a lot faster than that long integral process. Now, as I mentioned earlier, integrals are the opposite of derivatives. This means that any of the quick derivative processes work backwards for integrals. So i.e., for derivatives, we had sine of x, and the derivative of that was cosine of x, which went to negative sine of x, which went to negative cosine of x, which went to sine of x. So, going down, we have derivatives. However, going up, we have integrals. So, the integral of sine of x is negative cosine of x, and the integral of that is negative sine of x, the integral of that is cosine of x, and the integral of that is sine of x. So, it works backwards. Now, there are other things like this. For example, the integral of 1 over x is the natural log of x. And, of course, the integral of e to the x is still e to the x. Now, this works for all of the quick derivative processes. These are just the most common. So, if you happen to come across the end product of any of the other quick derivative processes, you can just write the start product of those. However, it is much less likely that you'll come across secant squared of x, for example. Now, for quick derivatives, there were a series of functions that would allow you to take certain derivatives. For example, you had a certain function for if you were multiplying a function by a function, another process for if you were dividing a function by a function, and yet another one if you had one function inside of another function. Now, for integrals, there was only really one of these processes, and that is U-Substitution. Now, to explain U-Substitution, I'm going to have this integral, so we're going to integrate sine of 2x. Now, if this were a derivative, we would use the chain rule because there is a function inside of another function. However, for integrals, we do not have the chain rule. As I mentioned, we are using U-Substitution. What you do for U-Substitution is you replace a section of the entire function with u so you can actually solve that function. So, in this case, we're going to replace the 2x with u. So we will set u equal to 2x. And then we write this, so we're now integrating sine of u. Now, notice there is a bit of an issue. So we have made this a much simpler function, something we can integrate. Integrating sine of u is rather easy. However, we're integrating it with respect to x. We need to have this be with respect to u. So this needs to be du, not dx. So, to do that, we're actually going to use some derivatives. So, looking at this equivalency, we're going to take the derivative of it. So the derivative of u is simply the derivative of u, du, and the derivative of 2x is 2 times the derivative of x. Now, notice here we have our du, which is what we want, and we have our dx, which we can use to get rid of this dx. So, to do that, we are going to get this, divide both sides by 2 to get this dx alone. So we have dx equals du over 2. So, now plugging this into our integral, we now have the integral of sine of u du over 2. Now, taking the integral of that, we get negative cosine of u over 2, plus c, of course. Now, the last step we need to do is we need to get rid of this u. So to do that, we'll simply look back up here and replace our u with the 2x. So, that leaves us with negative cosine of 2x over 2 plus c. So, the integral of sine of 2x is negative cosine of 2x over 2 plus c. And if you take the derivative of this, you'll see you get that. Now, U-substitution is, however, limited. There are certain functions that you still cannot integrate even with U-substitution. Because for U-substitution to work, you need to replace all variables with U. All of them. And even if you do manage to replace all the variables with U, you'll still need U as one function, not multiple. So this creates certain limitations for U-substitution. But yeah, so that was my video on quick integrals. Hope you enjoyed it, hope you learned something, and see ya!